This video demonstrates how to use Mech-DLK to distinguish defects from similar interferences in images, enabling precise and efficient data labeling and model training. In defect segmentation scenarios, defects can sometimes appear highly similar to certain normal areas, causing interference during model training. Therefore, using the mask tool to cover normal regions resembling defects is recommended to ensure the model identifies defects accurately. In this example of chip image defect detection, the goal is to recognize and locate excess solder defects outside designated solder joints, determining whether the chip is qualified. However, the 4 standard solder joints on the pads closely resemble the defects in appearance and reflectivity. Drawing the mask to cover these areas will effectively eliminate similar interference and improve the model's defect recognition accuracy. The overall workflow consists of 6 steps: data collection, data processing, data labeling, model training, model validation, and model export. Now, let's go through the specific process. The first step is data collection, which is the preparatory work. During image acquisition, adjust the 2D exposure mode and white balance settings to improve image quality based on project requirements. In addition, adjust the amount of data collected based on defect types and their degree of variation. After collection, select only high-quality images for labeling and training. Please refer to our documentation for details. Next, proceed to data processing. Open Mech-DLK. Create a new project. Select the Save path. Once in the project interface, add the defect segmentation module. Import the pre-filtered image data. First, browse through the images to identify the shape, location, and other characteristics of the defects. Observe that the excess solder defects are concentrated only in the central area of the image. Therefore, set the ROI to reduce interference from irrelevant background. After drawing the ROI, further verify that defects in all images are fully contained within it. Additionally, note that the solder joints appear in relatively fixed positions across the images. Apply the global mask to exclude their interference. After drawing, check that the mask fully covers the solder joints in all images. Move on to data labeling. First, create classes based on the defect type or feature. For this scenario, only one type of defect needs to be recognized, necessitating a single class. Excess solder defects vary in quantity, position, shape, and size. In this case, only select a small number of typical defects with distinct variations for precise labeling. This sufficiently covers key features and meets model training requirements. Utilizing the Smart Labeling tool can further enhance efficiency. Simply click on the defect to be labeled, make area adjustments as needed, and press Enter to apply the labeling. Now, 9 labeled images are available for initial training. Move them to the training set. An OK image can also be included for the model to distinguish between defective and normal workpieces. For this, select one defect-free image, label it as OK, and move it to the training set. Then, split the data into training and validation sets. A typical split is 80% for training and 20% for validation. After completion, proceed to the training phase. Configure the training parameters according to the actual needs. Ensure that the adjustments in data augmentation parameters don't affect defect features. Brightness controls the overall lightness or darkness of the image. As the lighting conditions during data acquisition can't cover illumination variations throughout the day, expanding the brightness range enhances the model's adaptability to different lighting environments. Keep the default settings here. Contrast adjusts the grayscale variation range in images. In this scenario, appropriate contrast adjustment can make defect regions stand out more clearly. The default contrast setting is sufficient to meet the requirements. Next, adjust the parameters related to object pose, including translation, rotation, and flip. Translation shifts the entire image horizontally and vertically by a certain distance. Rotation pivots the image around a point at a defined angle. Flip performs a 180 degrees horizontal or vertical mirror transformation of the image. The defect characteristics in this project are unaffected by translation, rotation, or flipping. Therefore, enable all three parameters and adjust them appropriately to ensure the model recognizes defects in diverse orientations. Scale resizes images proportionally, either downscaling or upscaling it. Given the varying shapes and sizes of defects in this scenario, appropriately adjusting the scale parameter improves model generalization capability. Then, configure the training parameters. Considering the defects are relatively large with clear contours, select high speed for the model type to improve training efficiency. Also, increase the epochs appropriately to observe the model's accuracy curve and select the best model. The input image size should be adjusted in line with the image and can be set later. The other parameters can remain at their defaults. Click OK to save the settings. On the main interface, we're able to preview resized image. This facilitates the tuning of input image size. Minimize the size as much as possible to speed up training, provided that the defects and labels remain clearly visible. Here, 256 by 256 suffices for clarity. Once parameters are set, start the training. During training, it's convenient to monitor the training accuracy curve and assess if the results meet the required precision. Now that all training epochs are complete, observe that the accuracy stabilizes and the loss remains low, satisfying the requirements. Next, evaluate the model's performance based on the validation results and segmentation outputs. Using validation statistics and defect inference results, check for any missed or incorrect detections. Start with the training and validation sets. Currently, both sets demonstrate good recognition performance. Then examine the test set, which is used to evaluate the model's generalization and requires close attention. Upon inspection, the segmentation results for the test set are generally accurate. One false detection is found in image 29, where the model incorrectly identified OK data as defect. To address this, first label the image as OK. Then, add it to the training set for retraining and validation. If missed detections occur, additional labeling is required. Be sure to label both detected and missed defects within the image before adding it to the training set. This case shows no missed detections. Labels can be added in small batches through repeated iterations until all detection results are satisfactory and the model performs well. Then, retrain the model. Again, ensure the ratio between the training and validation sets remains within an acceptable range. When finished, validate and check the data as before. Upon inspection, all the data meets the criteria for this scenario, and the model is qualified. Subsequently, export the trained model. This completes the training of a defect segmentation model that efficiently excludes similar interference. For more details, please refer to our documentation.